Alright, so today is about using the calculator and maybe some other computer tools to create a line of best fit. And the first, I guess, vocabulary word for today is called a linear regression. All a linear regression is a method that like a computer or a calculator would use to find a very precise line of best fit. And we know that we've been talking about the line of best fit already. It's just a line that models a set of data. What we know, or what I want you to know, there's only one best line of fit for a set of data. We can have many lines of fit, but there's only one that's best. One little comment here with the vocabulary word linear regression is the way that I remember it, regress or regression means to go backwards. So here it's a method, again, of where I would have a data set. So I have a data set here, and this table shows the number of free throws you would make based on how many days of practice you've gone to. So here I'm starting with a set of data, and I'm going to go and try to fit a line to it, rather than what we traditionally do is kind of go backwards, where maybe we have a line, and then we use that line or that equation to plot a bunch of points. So here the computer's just going backwards. It's taking our data to come up with a very, very precise line of best fit, and it's the best line of fit that it can possibly come up with. And that brings up an important point. So like, let's say we have this data set. What we've been doing, or what we can do, is we can find a line that models this data set just by hand is what we call. So we can just do it ourselves. Pick a few points, find a good slope, and then model that. So for example, maybe a student would come up and do this. I think this is a pretty good line of best fit. I think what it shows, it goes through a couple points. What I can see is there's 5 points below that line, there's 4 points above it, and I do think it fits the overall trend of the data. I think that's a great line of fit if you did that by hand. Another student, though, could have done this red one. I also would argue that this is a pretty good line of fit. It doesn't go through as many points, but there's still, now there's 5 below, and then there's 5 above. So this student didn't have equal numbers above and below, but it went through more points. This student had equal numbers above and below, but it went through less points. So the question here would be like, well, what line of fit is best then? We can't have multiple lines of best fits that are the best. There's only one of them. And the way that we can start to determine what line of fit is best, or just in general, how do I know if my line of fit is good? So then obviously the one who fits it the best, or who has the, this is a weird language, but the one who fits the best would be the best line of fit. But if I fit it good and you don't fit it good, well then obviously my line is better. So the tool that we have to help us with that is called the correlational coefficient. And all that is, it's a numerical measurement, and we call it the letter R, and that value of R will only fall between -1 and 1, so as like an inequality. This correlational coefficient will be some value between -1 and 1, and it helps us decide two different things about our line of best fit. So one, it'll tell us the type of the type of correlation. Will it be a positive correlation or will it be a negative correlation? And then it also tells us how closely or how good an equation models the data. So for example, if I have an equation that models it really, really, really well, the correlational coefficient will tell me that. If I have a line, let's say, like this one here in orange or in black, clearly doesn't model the data, the correlational coefficient would give me a number that would tell me that doesn't model the data. So again, it goes between -1 and 1, and there's two things that we have to look at here. So the sign of it, whether it's positive or negative. So we know if it's positive or negative, that'll tell us the type of correlation. So if it's a negative number, then we have negative correlation. So that's what this image over here is showing us. Anywhere below 0, so these are the negative numbers, are going to be negative correlation. If that number was positive, so like positive 0.75, we know that there's a positive correlation between those two data sets. So the next thing is the value of it. So the bigger the number, the stronger the relationship. So for instance, I have a couple examples over here. So if I look at something like -0.75, what that would tell me is the correlation is a negative correlation. That's just the sign. So just the sign would tell me what type of relationship there is. But then I look at the number. The actual number itself is 0.75. So that's going to tell me how good or how strong my equation models the data. So the general rule of thumb that we will use, so on this little image here, our cutoff is going to be about 0.8, in either direction. Again, we're not worried about the sign. But if I have 0.80 or above, we're going to consider that a strong correlation. If we have anything between 0.8 and something like 0.5, which I guess I should move over a little bit. Anything between 0.8 and 0.5, so let's put 0.5 on there, we'll consider just a weak correlation. So anything in there we'll just classify as weak. So we want to see above 0.8 to be strong. So like here, 0.75 would be not quite at 0.8, so I'd still call this somewhat of a weak or medium correlation. Now the important example is right below it. R is 0.75, so here the correlational coefficient just has a different sign. So here we'd have the same two things we would look for. So the first thing we would see is that since the number is positive, we'd have a positive correlation. But again, all we care about is the value of the number. I don't really care about the sign in front of it. So negative 0.75 and 0.75 would actually have the same strength of correlation, I guess I would call it. Because again, the sign just tells us the type of relationship, or in other words, just like the slope of our line we'll start to see. So negative and positive won't really matter the difference. They have the same strength of correlation. Now, perfect correlation is 1 or -1, so that's all that these examples are here. So -1 and +1 are both perfect correlation. That means that the equation that I just wrote to model the data is exactly perfect. Anything that I put into my equation will be the exact data point that I get out. And again, the only difference here is the type of relationship. When one of them is negative, that's just meaning the relationship between the two is decreasing. So maybe the graph looks like that. If this one was positive, that just means the graph is going up. So again, the correlational coefficient is a way that we can determine how good our line of best fit is. So for example here, let's say this black one had a correlational coefficient of, let's take a picture of this. Let's say the black one had a correlational coefficient of 0.79, and the red one had a correlational coefficient of 0.81. The one that has the higher value, so they're both positive, which we can see they're increasing, but since this has a higher R value, that would mean that my R is a bigger number, which means that line of best fit in red is a better line of best fit than the black one based off of what the computer would tell me. And again, the computer is the only thing that'll tell us the correlational coefficient for right now. So that'll be something the computer or our graphing calculator will always tell us. So again, now what we have is we have a way to write a line of best fit and then determine if it's a good line of best fit. And ultimately the goal we know is that when we write a line of best fit, when we write a line of best fit, the ultimate goal is to, I would say, use that line of best fit to answer some questions that we don't have the ability to see in our data. So for example, if I go back to this data here, I have a bunch of data for people who can shoot, who've gone to practice for a couple days, but maybe I don't have anybody on the team who's gone to practice more than 10 days, but I still want to know how many free throws do I think they would make? Well, I can use my line of best fit to predict that. So for instance, like if I just use the red one, just because I just said before the red one is better, just randomly, so I'm just going to use the red one. Here, so if I wanted to know, well, how many would I make if I went to practice for 10 days? I don't have that data point, but if I follow my line at 10 days, my line predicts I would make about 11 free throws. So again, I'm using my model to answer a question that I don't know. So there's two different types of questions that I could answer with the model that I've created. One of them is called interpolation. One of them is called extrapolation. And the only difference is where we are making our prediction. The type of prediction we make is kind of important. As we might investigate later, if we're predicting within data we have versus trying to predict some information about data that's really far away, then the difference in like how good our model will be eventually might change. So we want to describe what type of prediction we're making. So interpolation is when we use our line of best fit to make a prediction between the data points that we have. So for example, on this graph here, I have data points between between the x value of 2, or the days of practice, and then I think my last data point is right here. So if I use my line of best fit to make a prediction somewhere in between those number of days, so I have information between 2 and 9 days, so maybe I could predict, so like for instance, if I go to the data here, maybe I want to know some information in between there. And maybe I have all I need, but what if I said, what does my model predict that I would get for 5 days? So if I use my model for 5 days, 5 days is within the data that I have. So I'd call that interpolation. Extrapolation is our other word. And extrapolation is using your model to make a prediction about, or make a prediction outside of the data. So for instance, if I wanted to know, like my original question, what about 10 days? I don't have any data about 10 days, and that's beyond the data that I've collected. So I'd consider that extrapolation when I make a prediction over here. I could also make a prediction on the other side of my data, because again, I don't have any data that's less than 2 days. So maybe I want to know, like, how many free throws would I make if I have no practice? Well, since that data point, or that x value, is outside of the data that I have, that'd be extrapolation. If I wanted to know something, like I said before, like 10 days, I don't have any data about 10 days, and it's outside, or in other words, bigger than the data that I do have, so I consider that extrapolation. And you're not responsible for the rest of that sheet here. So again, just summarizing, we're going to be using calculators and technology to create lines of best fit. When the calculator does it, it's called a linear regression. The calculator then is able to give us the best line of fit that it could possibly make. And the way that it determines that is by calculating an R value. And R value tells us how good or how well our model, in other words, our line, fits a set of data. It tells us 2 things: the type of correlation, whether it's like a positive correlation or a negative correlation, and it tells us how good it does that. And again, we know that on this little kind of diagram here, we have to separate the values from the positive or the negative, because positive tells us it's uphill, negative would tell us it's downhill. The values after the positive or the negative is what determines how good our relationship is. Now, when we write a line of best fit, we can have the calculator give us the best one it possibly can. It'll give us the R value to say how good it actually is. We can use that line of best fit to make predictions. When we make a prediction within data that we have, we call that interpolation, and we make a prediction about data or information without or outside of the data that we currently have, we call that extrapolation.